Okay, so if you weren't convinced that this was a hard calculus class and that we haven't done much algebra yet, I promise you this is the section where we're going to start ramping up the algebra, and ramping up the more complicated sort of things in this class. So we're going to talk about tangent lines, which we have kind of talked about before. Oh, yeah. Anyone else need the notes? And we're also going to talk about the thing called a derivative, which we explained about last week, which was kind of a while ago. I told you about Isaac Newton's experiment that he did, which actually isn't his experiment. Please don't fact check on me this. But basically, he did this experiment to find the slope of a tangent line at any point of any graph. So as long as it, even if it had a curve, we could find the slope or the instantaneous velocity of a specific point in that graph. Okay, and the way we did that was we used this thing called the secant line, which has 2 points on the graph instead of just one, to approximate the slope of the tangent line. Okay, so for example, if we had a curvy graph that looked like this one, and we were focusing on the point A, okay, f of A, f of A, and we wanted to find the slope of the tangent line at A, we took the secant line and we looked at that slope, and we basically took the limit of the slope of the secant line as it got closer and closer and closer to A, okay? The slope of the secant line turned into this crazy thing, and the slope of the tangent line turned into this crazy thing. We called this several things. We called it the instantaneous velocity of f at a point A. We also called it the derivative of f at A. And we also called it f prime of A. So we have all these different types of ways to say this. I want to add one more thing that we use to define this. If the function is y, so if the original function is y, we also might call this dy over dx, or d over dx, gosh, of y. Okay, so some other ways that we might say this. Okay, so in other words, the derivative of a function f of x at x equals a is this value. Did you want me to go back? Yes. Sorry, I wrote that way too fast. Now, when I get excited, I kind of just like talk really, really, really fast, and I can't slow down. So thanks for stopping me there.
That says an original function is y.
Mm-hmm. And we call this thing, this crazy thing, or the derivative dy dx, or d over dx of y.
Where's these stand?
That's a good idea. I actually don't remember. Is it delta? It is delta, isn't it? Huh. Look at that. I learned stuff from my students.
Delta
Yes.
y over delta x times delta over delta x.
So John actually reminded me, it's called delta because delta is the symbol for change. Slope is rise over run, so it's the change in y over the change of x. Thank you for reminding me of that. I kind of blanked there. All right, that was a good question. Any other questions? All right. Oh gosh, I flipped too fast. Okay, so we want to find the derivative of any function. This is the definition of the derivative. So I know if you've taken a calculus class before, you might know that there are shortcuts that we can take, but we can always fall back on this definition. And I will require you to use this definition to find some derivatives. Okay, so let's just go through a few examples of this. So first, we have this big function x squared plus 2x plus 1. If I graph this, it would look like a parabola, right? So I can't just find the slope at any point, okay? We want to find the instantaneous rate of change, which is also the derivative of our function at a equals 1. Okay, so I want to find essentially f prime of 1, okay? So before I go on, let's actually find what f of 1 is. Okay, so I want to know what f prime of 1 is. let's find what f of 1 is, okay? What would that be? 4, good, and we got that by plugging it in, right? 1 squared plus 2 times 1 plus 1 is 4. Good. Okay, so I want to find the slope of the tangent line at the point 1, 4, right? X is 1, y is 4. That's what I want to find. Okay, let's use our definition. Okay, so I know that f of 1 is the limit as delta x goes to 0 of f of, okay, what is a here?
4,
Not 4, but
1.
it's not delta x, it's actually 1. Okay, yeah, because we want to find f prime of 1. 1 is a. We want to find f prime of a. Okay, so let's plug in 1 instead of a plus delta x minus f of, well, a is 1 over delta x. Okay. So all I did is I plugged in 1 for a, and I have, oh, sorry, this is f prime of 1, sorry. Okay, so I want to find what this is. Okay. So I know what f is. Why don't we just start plugging in our values, simplifying things out? Okay. What is f of 1 plus delta x? Good question. Okay, I know what f is. I know f is x squared plus 2x plus 1. And let me write that out. So f of x is x squared plus 2x plus 1. What's the f of, I don't know, t? What f of t? Good, t squared plus 2t plus 1. What would f of star be? Star squared plus 2 star plus 1. Okay, what's f of 1 plus delta x? Good, okay. So all this is saying is take whatever's on the inside of the parentheses and plug it in for x. Okay, so that's all we're doing. Okay, so f of 1 plus delta x here is 1 plus delta x squared plus 2, 1 plus delta x plus 1. Okay, so all of this that I wrote here, all of this is f of 1 plus delta x. Okay. All right, I know what f of 1 is. I just found it, right? This is f of 1. We said that was 4. So I'm just going to plug in f of 1 here. So this guy is f of 1. Okay. And I forgot to make this all over delta x. Okay. Now, I know a lot of you might be confused looking at delta x because there's 2 symbols there. Delta and x aren't separate entities, okay? Delta x by itself is 1 variable, okay? So delta x is basically anything like x, t, y, z. It's just a variable, okay? All right. Any ideas on how to simplify this out a little bit better?
Combine like terms and then take out a delta x.
Okay, I like, you kind of are blowing through the steps with me here. I do want to show some more steps, but that's a good idea. If I want to combine like terms, maybe I should FOIL out something first, right? Now, a lot of things I see students do that is a mistake is taking the 2 and moving it in, like distributing it to the 1 and the delta x. This is where our algebra skills come in, right? We can't do that. We have to FOIL it out. Okay, so you might be able to do this in your head. I'm actually going to write out the step of writing 1 plus delta x twice. Okay, because I can't do this in my head. I always mess up. Okay, so that's 1 plus delta x squared. Okay, what can I do with the 2? 2 times 1 plus delta x. What can I do with that? Distribute, good. So I can take my 2 here and move it to the 1 and the delta x. So plus 2 plus 2 delta x. Okay. And what's 1 minus 4? -3, good, -3. Okay, so I did as much as I could do on the top so far. And this is all over delta x. Okay. Looks like we can FOIL now, right? We got 1 times 1 times delta x is 1, and delta x times delta x. So let's do that now. We have the limit as delta x goes to 0. 1 plus 1 times delta x is just delta x plus delta x again. What's delta x times delta x? Delta x squared. Okay, so that's all that is. Okay, we have plus 2 delta x minus 3 all over delta x. That was the 1 minus 4 here. So I had a plus 1 and a minus 4. 1 minus 4 is -3. Lots of stuff to keep track of, right? Okay. Okay, so Michael said combine like terms, which is a good idea. Gets kind of hard when there's a lot of different stuff moving around though. So let's kind of go through the slope, okay? We have a delta x squared. I think that's pretty easy to isolate. So there's no other delta x squared, so let's just write that by itself. Okay. Looks like we have some delta x's to combine. So why don't we combine these together? We have a delta x, and a 2 delta x. So how many delta x do I have now? Good, 4 delta x. Okay, and then we have a 1 plus 2 minus 3. What's that? 0. Good, not gonna write that. All over delta x. Almost there. Here's where things get a little funky. If I plugged in delta x equals 0 into my function, it would be a 0 over 0 type limit, which means we have to do a little bit more work. When we have rational expressions, remember, factoring is the way to go. Is there a way I can factor the top?
Yeah,
How do I factor it?
take out delta x from the top.
Good, so delta x, and what am I left with on the inside?
Delta x plus.
Good. So just like factoring any polynomial, except that we have delta x instead of x. Okay, so delta x goes to 0. On the bottom, we have delta x. Looks like we can cross out the top and bottom, right? So delta x crosses out, delta x on the bottom crosses out, and we're left with the limit as delta x goes to 0 of delta x plus 4. Now we're at a place where we can just plug in, right? So just like we did with limits, with anything, we just have a delta x instead of an x. I'm just going to plug in 0 for delta x. Looks like my limit here is 4. Okay. So I did all of this work. I plugged it into my equation. I basically FOILed things out, combined like terms, factored out a delta x, crossed them out, and I'm left with my derivative at 1. We will talk more about what this derivative actually means later. But how about this? I'm going to give you another example to work through. If you flip the page, you'll see example number 2. I want you to try this example. I want to come to the front here. I'm looking around. Some of you have really good answers. I think some of us are a little bit, the algebra is getting a little too algebra-y. But let's kind of go over this real quick. Before I let Mason kind of go through this real quick, I want to talk about, okay, we know that the function is pi x plus the square root of 5. We want to find the derivative at -1. Now, that kind of changes what we did in example 1, because in example 1, we wanted to find the derivative at +1. So that's why our equation kind of looked like this with a +1 here, okay? Now that we're finding the derivative at -1, we want to find f of -1 plus delta x. Okay, so we're plugging in -1 instead of +1 now, okay? Well, I'm going to take one step and then I'll let you explain. I think what Will did is he found f or t of -1 first, which was -pi plus the square root of 5. Okay, I think everyone was good on that page. Will, do you kind of want to take us through the rest of your steps here?
Yeah, so for the first line, I just set up the equation where we plugged in -1 for like the x in f of x.
Mhm.
And then after that, I plugged in what my f of x or y was, which would be pi times the equation
Mhm.
-1 plus change in x, and then plus √5
Mhm.
minus f of -1, which we know is negative pi plus √5.
Mhm.
And then after that, I, in my head, basically distributed the -1 in front of the negative pi plus √5. So you could do +5 minus √5, and then you're left with pi times -1 plus change in x plus pi. And
Mhm.
then you can take out a pi from both terms, and then you're left with pi times -1 plus delta x plus 1, and then 1 plus -1 is 0. So you're left with delta pi times delta x over delta x, and then you just cancel out delta x and delta x.
Nice job. Very good. I think the one thing I've seen by walking around the room is a lot of people forgot to distribute the negative to both of the terms in the right. Okay, so that's something you might want to keep an eye out for. Some other things that I saw was forgetting to put the -1 instead of changing the question from example 1. Lots of algebra going on here. I think the best thing to do for these types of questions is just to go through a lot of practice questions. A lot of this is pretty much the same from question to question. A lot of this doesn't really change from one question to another. I recommend a little bit more practice. We'll do a little bit more in a different way though. Okay. If we flip our question, oh, did anyone have any questions on example 2? Yeah, yeah. All right. All right, let's flip our page to example number 3. Example number 3 is talking about something a little bit different, okay? We talked about a derivative of a function at a specific point. Now we're going to talk about this thing called the derivative function itself, okay? Sometimes we're not really interested in the derivative at any specific point, but we want to find the derivative at any point, okay? When we want to find the derivative at any point, we have this thing called the derivative function, okay? So if y is f of x, for example, we're going to call the derivative function f prime of x. Okay, so not f prime of a, but f prime of x, because we're talking about a function. And the derivative function has a very similar formula to the derivative at a point, except instead of a, we have x. Okay, so we're just replacing any point a by x. Okay. So let's talk about how to find this derivative function, what it actually means through example number 3. Okay, so here we have f of x, which is x squared plus 2x plus 1. We want to find the derivative of this function at x. Okay, so let's just write out this function. We have f prime of x. We know its definition is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Okay. Here's where it gets a little bit more fun because we have x's and we have delta x's. X and delta x are different variables, okay? So we can't combine them or do anything. We can't really mix them together, okay? All right, let's go through this. What is f of x plus delta x? Michael?
Would that be
Oh. Yeah.
Sorry, did somebody raise their hand?
No, you're good. Go ahead.
Theoretically speaking, wouldn't that just be x squared plus 2x plus 1 plus delta x?
Oh, so you're saying it's x squared plus 2x plus 1 plus delta x? What you just found is f of x plus delta x, right? Now, f of x plus delta x is different than f of x plus delta x,
Yeah.
but that's a good guess. Michael, did you want to say something?
X plus delta x squared plus 2x plus delta x plus 1.
Good. Okay, so f of x plus delta x is literally plugging in this weird thing instead of x, right? We're plugging in x plus delta x whenever we see an x. Okay. Does that make more sense? Nice. Okay. The second part says we're going to subtract off f of x. Well, f of x is easy because we literally have it up in the question. We're subtracting off x squared plus 2x plus 1. Okay. Now, I recommend putting parentheses around this thing that we're subtracting off because a lot of people kind of mess up in the signs. If you make a sign mistake, it might mess up you actually being able to get like an actual function at the end. And we'll talk about that a little bit later. Okay. So what I just did is I plugged in f of x plus delta x, and this thing over here is f of x. So I'm just subtracting the two. Okay. All right. Looks like we can do some stuff with this. Now, am I going to take this 2 here and distribute it to the x and the delta x? Is that what I'm going to do here? No, right? Okay, that is the mistake I see a lot. This is telling us to FOIL out x plus delta x, okay? Because I make a lot of mistakes, I'm going to write x plus delta x twice. Okay. What am I going to do with this 2? This one right here. That one's the one we distribute, right? So when we multiply by a number, we can distribute it. Exponents don't get distributed. Okay, so we have plus 2x plus 2 delta x plus 1, okay? And since I have a minus sign and a parentheses, let's just distribute that negative around. So we have minus x squared minus 2x minus 1 all over delta x. Okay. Are we good so far? Good. All right. So we have the limit as delta x goes to 0. Looks like we can FOIL out some stuff here, right? Let's do the FOILing part. Let's do this. We have x times x, which is x squared. We have an x times a delta x, another x times a delta x plus delta x squared. Okay. We have a 2x plus 2 delta x. Okay. Actually, I think we can, let's just keep everything how it is. So plus 1 minus x squared minus 2x minus 1 all over delta x. So we have a lot of stuff going on here. Okay. Let's see what we can simplify. We've expanded everything. Let's see if we can make things simpler. Okay. Let me just talk about something real quick. Okay. We have an x squared and another negative x squared. We also have a delta x squared going on. Can I combine delta x squared and x squared? No, I hear yes. No, right? Delta x is a separate variable. It's kind of, it's a different type of variable than x is. So we can't combine x squared and delta x squared. They are 2 separate little entities. I can combine the x squared and the minus x squared though. And those cancel out, right? Oh, no, you're fine. There's a lot of stuff going on here. Okay, so let me cancel out the x squares. Okay. The only other squared thing I have here is the delta x squared. And well, I can write that one down, right? Oh gosh, that's not what I meant to do. Let's do delta x squared. Okay. let's talk about what else we have. We have x times delta x. Let's talk about those. Looks like we have an x times delta x, another x times delta x, and there's no other x times delta x's. So let's combine those two, and we can't combine them with anything else. So we have two of those. 2 times x delta x. Okay. Are we good here?
No, still two delta x.
Oh, yes, there's still a 2 delta x, but I can't combine that with the x delta x. So let me write that one separately. Let me make another one here. We have this guy here, 2 delta x. Okay. What else can I do?
Oh, delta x.
I
You can take a delta x out of the entire equation.
good, but let's just keep going with this step. I know we're pretty much done. We have a 2x here and a minus 2x. Those cancel out, right? And we have a 1 and a minus 1. Those cancel out. Okay. And this is still all over delta x. Okay, Zach, what was the next step?
Taking a delta x out of everything.
Yeah, right. Everything in the numerator has a delta x attached to it. So we can factor out a delta x. Okay, so this is the limit as delta x goes to 0. Okay, what am I left with on top if I take out a delta x?
Delta x plus 2x plus 2.
Good, delta x plus 2x plus 2. Okay, on the bottom, we still have a delta x. Okay, looks like we can cross out the denominator and the numerator. So we're left with the limit as delta x goes to 0 of delta x plus 2x plus 2. Okay. Here's where things get a little tricky too. What is actually going to 0 here? Is it delta x or x? Delta x. So what am I going to plug 0 into?
Delta x.
Delta x. Am I plugging in 0 into x?
No.
No, right? I'm leaving x alone. Delta x is the thing going to 0. I'm going to plug in 0 in for delta x, but not x. Okay. So this is 0 plus 2x plus 2. I'm not plugging in to x. I'm plugging into delta x. Okay. Well, that's 2x plus 2. This is my final answer. Okay. So I know that f prime of x is 2x plus 2. We call this the derivative function because it tells us what the derivative is at any point, okay? What's the derivative at 1? 4, good. 2 times 1 plus 2 is 4. So instead of plugging in, okay, I want to find the derivative at 1, you have to do the whole thing and plug in a equals 1 into this whole thing. You can just find the derivative function and plug in 1 into the derivative. Okay. Any questions on example 3? I know we just went through a lot of algebra. I know, David, there's a lot of stuff going on. Mason?
Are we ever going to be able to use the shortcut of this for the nx and minus 1?
We'll learn about shortcuts this week. Yes, there are shortcuts. I will tell you, on the test, I will put something that tells you to use the derivative, okay? The definition of a derivative. You will have to do this once on a test, okay? Because we do have to know the definition of a derivative.
Plus 1 or any constant doesn't matter. The y-intercept doesn't.
Yeah, the plus any constant doesn't matter with derivatives, right? And we'll talk about why that's true next class. You know what? I'm going to give you guys some time to work on example 4. We might not get to actually solving it, but let's try it. I don't know if we have enough time to go over this. How about this? We're going to save this for next class. I'll have Michael go over his solution on Wednesday. And I guess I'll see you on Wednesday.